All right. Hello and welcome to another episode of Spreadsheet Wars, otherwise known as the Celestial Theodolite update number 14. Today we're going to get into an analysis on the data. I'm going to go over the spreadsheet, show everyone where I'm at on it. It's kind of a community project of sorts. A lot of people have contributed bits and pieces to it. So shout out to the lads and ladettes who have contributed. If anyone feels that the globe is not being represented correctly, please let me know. And if possible, if you know how to correct this spreadsheet or add whatever you want, add the instructions for what you would like added, and we will do the necessary comparison. If there's anything that you find wrong with the spreadsheet, et cetera, let me know, and we'll go through and fix it. So this is supposed to be kind of like an open source interpretation or an open source framework in which we can interpret the data. So any possible variable that you want to see extrapolated out of these measurements that we have, occlusion timings, peaks, distances, elevations for the stars with respect to stellarium times at the time of occlusion, locations, everything that you would ever possibly need can be referenced there. And then we have a nice clean computation sheet that can be used here. This tab over here is a legend. It'll be more filled out and things will be explained better when you go through it at some point when I get some more time. But yeah, hopefully the idea here is you'll be able to reference everything on this spreadsheet and interpret and use it to interpret the data that is in the data table here. So I'm going to kind of give a walkthrough tonight of everything that has changed and everything, like how to use it, what it looks like. So suppose you want to add a new star, you would just come here, fill out this column. It'll automatically complete into this new table based on the name of the star and the name of the mountain peak. Everything else will be put into this table automatically in there's a drop-down menu that associates the peak with the star, so only the relevant stars will show up when you select the relevant peak. Everything will take care of itself there. If you want to make a copy and use it yourself or whatever, that's how you add to the data set. So to kind of go over here, what this pulls from here, we got the classic occlusion timing, the occlusion date. Well, that's pulling from the wrong value there. That's wait a minute. Yeah, that's okay. Well, that's pulling from the wrong value. That should be a date, not the distance. Does it have the distance correct? Where's it pulling
that is a date.
It could just be a formatting thing if you format it as a date.
Oh, it is a date?
Problem.
Okay, gotcha. I'll fix that later. Oh, I did convert them all to numbers. That's right. Okay. Well, anyway, that's the date. So we got UTC time, the person who did the observation. Shout out to Hefferon, Dr. Hefferon. We got the old peak latitude, longitude, observer lat long. And then from that, we got the distance, mountain elevation, and the peak elevation, the observer altitude, and the distance to the peak. And then over here, we have the sign of Aries, which represents the true position of the star. So we're referencing that angle with respect to the peak. And then we also include the refracted angle at the peak. We don't actually use that for any computational purposes, but that's just where it was at the time of occlusion. If we ever need to reference it, it's we have that information there. And then, of course, we have the true position with respect to the observer's location. And then we have the refracted position with respect to the observer's location, obviously still referencing the stellarium positions. So anytime you see epsilon or the sign of Aries, one of those will be the true position, and the other one will be the refracted position with respect to that true position at the observer location and or peak, depending on whatever we're referencing. So we have our difference in mountain altitude, and that'll be useful for how we're going to do our trigonometry to make our predictions. And then the outputs down here are the same as the decimal degrees up here, but it's just converted into degrees, minutes, and seconds because that's easier for me to look at. I prefer that method, but if you like the decimal degrees, feel free to ignore that. But every calculation that's in decimal degrees has a corresponding translation to. All right. And then down here, we have our standard refraction for the refraction lads, which converts 7/6R to the distance of the observation. We got Earth radius, and we have the old angle adjuster in case we ever want to adjust an angle just to see hypothetically what would happen if XYZ. I think if we adjust this one, it will adjust the gamma globe refracted angle there. and then the calculations for that will change. So you could see how how the calculations would change if you change the angle. But that's, obviously left at 0. And then we get over here to our prediction side, or for the computational output based on all the information that gets swapped around here when you enter your peak and star. So we have flat Earth prediction noted in blue and by this little triangle here. And for the example of Pike's Peak with all this information, we come up with an angle of 2 degrees 31 for the flat Earth prediction. And based off of the occlusion timing, we can do the distance times the tangent of the occlusion angle, and we can derive what the elevation would have had to have been, and we can then compare which elevation is closest to the true elevation. So from that, we can also do the same with distance. When we compare the mountain altitude to the occlusion angle, we can derive what the distance would have had to have been to complete that. And we see how far off we are in distance. And then we're going to do that for every star, and we're going to see how much we are off for what the globe predicts. So here's how we computate what the globe predicts. So since nobody could agree on it, and the whole methodology of this actually removes terrestrial refraction by mechanism of the fact that the light source is on the other side of the mountain, and once on your side of the mountain, you can no longer see it. The refraction between you and the mountain peak can't possibly lift the star light back over the mountain peak. That's incoherent. Obviously, there's no refraction. I mean, obviously, the refraction between you and the mountain peak isn't a factor. And all we care about is the angle in which we no longer see the star. If that angle, or the true position with respect to the peak is all we care about. And if that angle just so happens to line up with what the plane trig would be for that mountain peak, given the same information, then we go from there. 1 second, I have to clear my throat. All right. So, but nevertheless, the globularist asked us to include it. So we include it for analysis and comparison as well, even though it's not part of the raw globe, which is what actually does the occluding, which is the relevant part of the analysis. So, but anyway, we have the globe prediction here. So we have the drop over distance by doing the square of the radius squared plus the distance squared minus the radius. And that gives us 200 meters and drop over this distance here for 50,000 meters. We can convert that into an angle the same way we do like a rise over run. And we just use this 201 as our rise. And then we have our distance there. And it gives us the conversion to in an angle. So we can write that down in arc seconds there. So they predict 13 arc minutes in drop. And then we just subtract that from our flat Earth 231. And then they get 217 for their raw globe. So to figure out the raw globe angle, that's what you would use for what's actually going to do the occluding part of it. And then we that analysis diverges a little bit here because then we go on to show they're refracted. So the actual raw globe is continued down here with the actual Heffron analysis. But for the comparison of how they derive the raw globe, I just wanted to show that in every case, how Mike derives the raw globe and how the raw globe can be alternatively derived is the same in every scenario. So it's not strawmanning the globe. It comes up with the same exact prediction for how much drop over distance there should be. So anyway, the calculations for that are actually done by 180 times the observer distance over 2 pi r, and that gives how much drop over distance there will be. There's a secondary analysis that includes 360 times the distance to get an estimate on where the true position of the star would be. And sometimes that works out and sometimes it's off by a little bit, but that's like a secondary analysis that I'm looking into. The only one that we care about for this is the 180 times the distance, because that gives the geometric globe drop there. So anyway, we see the comparison there. And in this case, when we add the refraction difference back from whatever the actual refraction was by subtracting the difference from the true position and apparent position at the observer location, so we don't have to argue on what formula best describes the hoodly daddle. We can just get whatever was recorded in reality, whatever they said it was. So in this case, when we take the refraction amount and add it to the raw globe amount, it comes out to basically the flat Earth trig. And this relationship doesn't hold 1-to-1 on every observation, but it maintains a pretty close relationship, and I'm going to add a column here to track that difference there to see how much these refraction corrections are compensating to make it just appear like it's flat. So we'll get a better look into that as we move on. Let's see here. And then so we derive the mountain altitude and distance based off of the raw globe there. It's off by 201 meters, off by 5,000 in distance. And in the comparison here for the flat earth one, we were off by 36 meters and we were off by 800 meters in distance. And I also give some parameters in the analysis for how to, what's a good measurement, what's an indistinguishable measurement, what's a conclusive flat, what's a conclusive globe, etc. So we'll go over that here in a minute, but I just got to finish going over globe calcs here. So anyway, I also included epsilon globe here, which is the inverse of what we're doing with respect to the true position at the peak. We're doing the refracted position for the observer at the peak, or from the observer's position, sorry, at the time of occlusion. So whatever angle the star's refracted position was at the angle of occlusion, we'll do some trig on that and see what it is, because they predict that their true position would be 206 at this time, but it's refracted up by 16 arc minutes. So they predict it's actually 2 degrees 22. So we'll do some comparisons there to see how that fares. So this one's actually a little better, gives 125 and off by 3,000 there. And then there's a secondary analysis that I'm doing as well, where I'm incorporating spherical trig and referencing the latitude and longitude coordinates between them to derive the distance and all that, and see what they get off of that. And in this case, the apparent position comes off to be off by 70, and the distance comes off to be off by 1,000. So they're actually hella close. But remember, their refracted geometric angle to the peak is our natural raw angle. So that's hilarious that their refracted position gives them like a flat earth, like an accurate flat earth angle, identical, and then it gives them an accurate distance and elevation to the peak. Now this relationship doesn't always hold 1-to-1, but it's particularly close here because the angle is of occlusion was 232. So with their refraction added on, they come up to be what is it, 233. So it's a lot closer there in that regard. But yeah, we got a lot of stuff here. And then at the end here, we have a refraction analysis where we can see, so in the same way that we can calculate drop over distance and see and convert that to an angle for angular drop, we can also we can convert how much refraction, like, so we can take that 16 arc minutes in refraction and we can compare that to the distance as a ratio, and the tangent of that will give us the liftover distance. So the opposite of drop over distance, this will give us the liftover distance. So now we can directly see how much celestial refraction is impacting these measurements and the effect that they have, because we all assume, like, that the globe is constructed off of refraction corrections, but this is how we would kind of quantify that here. So what we can show with this is liftover distance, and this will be how much it's lifted. So we can do a comparison here. So remember, they predicted 201 in drop, but they get 240 in lift. So they create a difference of 38 there, which also happened. Oh, that's pretty close to how much we were off too. That's funny. But anyway, they have this, they're basically double their amount there. And then we have the celestial refraction position lift, true position minus apparent. So here we can build a comparison for where the true position, where the light source, so to speak, is with respect to the apparent position, and we could get like a clearance tolerance for how low that true position was with respect to the peak before the apparent position got occluded. So we could come up with a way to determine like what's a reasonable intersection period difference between in terms of angular difference between those two, before we can just say, okay, well, you're clearly just now refracting to infinity to like make it whatever you have to be to say that it's a globe, even though this is like a flat earth angle. So we can continue on here by showing the difference in clearance. So we have our geometric clearance by showing that ratio. So the difference in position of the star, true position at the peak, and the position of the star at the observer location is 27 arc minutes of, and that gives us it gives us a clearance of 27 arc minutes there. And then we have our difference in clearance, which is derived from that same thing. The difference in clearance is lift minus the clearance, right? So we can take how much was lifted and subtract that from the clearance amount, how much it would have had to have been at the point for occlusion, and see how much that comes out to be. And what we get with that is a ratio of overcompensation. So we can see with respect to like that occlusion at that peak elevation, how much refraction are they overcompensating for with this 240 amount over a drop of 201? Well, it comes out to be 101 or 119% for their compensation. And then the refraction compensation or overcompensation, which is just lift minus drop over the clearance, gives 443%. So their refraction is like, it's basically like, it just looks flat because it's super refracted up. Like, that's been their argument forever. But now we can just see how ridiculous that position is. Because what they're saying is, even though they predict a different occlusion timing, everything was just lifted up so that it just looks flat. That's preposterous.
Well, the other thing I like to point out, right, is that when you make them predict with refraction, it kind of confines them to these actual finite empirical measurements that we can calculate with known formulas, as opposed to previously when you make an observation and then they would do a post-diction based on all the details they could to manufacture the refraction coefficient that would bring that observation back into globularity. And when you remove that and make it a prediction, then it's kind of funny to see how all the different methods still fail.
Absolutely. And on top of that, we have, so I'm going to go over now. I think I moved it over here. Let me see if I can find it. Parameters. Did I delete it? 1 second. All right. I super deleted it. Oh, no, it's right here. Okay. So parameters for interpretation of the data, right? Because we're looking at a bunch of raw data and we're like, look, it's flat. And other people are like, look, it's globe somehow. Even though when we do our comparisons for each one of these mountains, we're going to, we can see the results don't favor the globe in the way that they would like it to. So they kind of confine it to just the angular analysis and whatnot, and they don't really do the distance and elevation thing, which is the purpose of it. So anyway, we run into some instances where the refracted angle is equal to the true position of the star at the mountain peak. And in that case, you will run into results that are indistinguishable from one another. It doesn't make the timing such that it proves the globe, because remember, the globe has to show a timing difference through its drop over distance, not refract compensate exactly to or very close to our position. So making the results indistinguishable don't falsify the null hypothesis. The null hypothesis method being, first we assume as our hypothesis that the Earth is a globe, and then we assume that for the null hypothesis that the Earth is flat, and then we have to falsify the null hypothesis with real world measurements. So when we do that with measurements that are indistinguishable from what a globe and what a flat Earth would predict, by metric of the refracted position being damn near identical to the true position of the star, that's an indistinguishable result. So the parameters that I came up with was, because the sky moves at 30 meters per second terrestrially, you could look at it that way. You in elevation, and because the elevations are kind of always close, you have to be 60 meters or better than the other prediction to have a definitive winner on who's actually closer. Because if it's within that tolerance, then you could chalk it up either way. Because as I was going over this spreadsheet and calculating the different things, I watched these variables change over and over, where it was closer to flat, closer to refracted globe, closer to, this one or that one. And then when you come up with a metric, though, to like actually interpret the data with an error tolerance, well, you get indistinguishable measurements. You don't get a measurement that's actually better than what the flat Earth would predict. And this comparison is using the refracted positions. So this isn't even the actual Heffron method. This is just for analysis purposes to satisfy everyone's and my own personal curiosity for what the distances and stuff would be using those angular relationships. But down here, we have the so I consider this an internal consistency test of the system because the system was built on the refracted positions of the stars, and that's what we're or that's what they're going to be referencing for everything. So I use that as their as a comparison for the internal consistency, and then for the external consistency, using the true position of the star, which is a star's calculated position with respect to its position on the vernal equinox, adding 15 degrees per hour to it. We go over the where that comparison is for the raw geometric globe, the thing that actually does the occluding, and flat Earth, and those angles pretty much always never work out, except for in the instance of what's it called, Blinn Mountain. It's an indistinguishable one here because the refracted position is equal to the other the apparent position at the peak. So there'll be an additional parameter set up for that, so that when it's indistinguishable, it's there'll be like an additional ruling on it to go from there. But just going off of and then so distance. So when we derive distance, you have to be within 1,600 meters, which is a mile. So if you're within, so you have to be a mile or better than the other prediction for it to display like globe or one of the globes as a winner here. So we'll go over a couple of things here. I see Ruhif anxiously awaiting to get into it by sharing his thing in the middle of me sharing mine, which is very rude, Ruhif. But I know you're just very excited. But we'll get to you in a second. So
I'm
I want
not
to
forcing people to watch my stream, Alan.
I know, but that's hella rude. So anyway,
Your mum was rude last night.
if you don't act like that, man. So anyway, we'll add a couple other peaks here. Actually, you know what? 1 second. We'll do, let's see. We'll do the Blinn Mountain ones because those are the most disputed weapons. And we'll do Getaway Mountain and Houndstooth here. So Blinn Mountain. We go over one of Jesse's here. We have the true position of the star at the mountain peak being clocked at 1 degree, 21 arc minutes. The flat Earth prediction is 1 degree, 34 arc minutes. The refracted position of the star at time of occlusion is 1 degree, 30 arc minutes. So 4 arc minute difference in the raw flat Earth prediction for it. And when we derive the distances and the elevations off the occlusion, raw flat Earth is off by 81 meters in elevation, and we're off by 3,400 in distance. And then they're off by 26 meters in distance, and they're 1,000 meters in, 26 in elevation, 1,000 in elevation. And what that looks like over here before we get to the refraction comparison is, given the parameters mentioned earlier for distance and elevation, we get an indistinguishable comparison going refracted for true position with respect to peak. And then for external consistency test, we were closer on the elevation, but they were closer on the distance. So we have a mix match here, and a mix match is a limit of use parameter. So that is the limit of use of our tool when these two are indistinguishable from one another. When they're within about 4 arc minutes, it looks like they're pretty much identical there. And when we get into the refraction compensation here, there was a lift. There was supposed to be a 38 meter drop over this 22,000 meter distance. And when we look at the refraction correction, they actually doubled it. They predicted what is it? 100. They tripled it. They predicted 130 meters in lift, 131 meters in lift. So in this comparison, like, does this prove a globe? Like, no, but it doesn't falsify the null hypothesis. It doesn't show that the method doesn't work because the clearance difference between the peak and the occlusion was three arc minutes. So the numbers that gave an elevation that correspond to the peak's actual elevation, there was a difference in the true and refracted position of 3 arc minutes, right? The globe would predict that it should still be refracted, because remember, this was an occlusion. So if it's refracted up and the true position intersection has no relationship to it, then the star should have been visible well before that. But there's a 4 arc minute difference between the true position and refracted position. So the methodology is entirely sound and proven, and we could use this difference that correctly derives the elevation to kind of calibrate a difference from what reasonable refraction looks like to what it looks like when it's just overcorrecting by thousands of percent to, or by hundreds of percent, to make it appear like it's flat. So that was blend, and we'll go over Getaway Mountain, I think. That was another one. So same scenario here. We have the true position at 45 with respect to the peak, and the refracted position with respect to the observer to the peak is 45. So damn near. So these give damn near indistinguishables as well, very close predictions. And then when you get into the raw, they're only off by 84, but their distance is off by 4,000 on the raw. But because of even though the distance is long, like it's 48,000 meters, but because the refracted position and true position are so close, the compensation is, it makes it indistinguishable. So they predict 800 or 188 meters of drop, but they have 370 meters of lift. So they're overcompensating by 182 meters. That's basically, what was that, like it's almost double their prediction. Or I mean, it's almost the same amount as they're predicting for drop is how much they're overcompensating for. So I think this creates a pretty interesting picture here, especially when we compare it to the raw positions, which is it gets more revealing there. But if there's any, let's see here. Is there any other ones I wanted to go over? Oh, North Peak. Oh, North Peak. So this was our largest distance yet. This was 130,000 meters with a occlusion angle of 1 degree. Oh, I'm sorry, 58 arc minutes. So just under a degree at the true position with respect to the peak. And then the apparent position with respect to the peak is 18 arc minutes. And their true position is 1 degree and 48 arc minutes. So they actually predict that this is beneath this is the negative coordinates that we've all been having a discussion about. So this is actually below the horizon by 11 arc minutes, I believe, on the conversion when you do how much they lifted it up. So when you go through that, we get the raw trig for what the flat Earth predicts, 45 arc minutes for our raw angle. And remember, their occlusion angle with respect to the peak, or the refracted position, was 30, that they lifted up by 30 arc minutes. So we're at 35, or we're at 45, they're at 30 with their refracted. But then so we get an elevation difference of 500 meters with the true position of occlusion timing with respect to the peak. We get a distance difference of 30,000 meters. And then for the refracted globe, they're off in elevation by 1,000, 1,100, and in distance they're off by 270,000. The refracted globe position at the time of occlusion with respect to the observer, like just whatever the observer sees, that angle gives them 1,000 meters off and 192,000 meters off in distance. And then following the raw trig, they're off by 1,300 meters. I'm sorry, the raw geometric position of the globe, the one that does the occluding. They're off by 1,300 meters in elevation, and they're off by 500,000 in distance. And then doing the spherical trig comparison with the refracted position, they're off by 330 meters in elevation and 13,000 in difference from my secondary analysis. And then what we have here, though, is a negative expected drop amount here, meaning the refracted amount failed to compensate for when the star was actually occluded. So that's a huge geometric failure for them because it's supposed to be, you know, under the horizon at that point. And even with their drop over distance or even with their celestial refraction to compensate as a refracted lift mechanic, remember they predict 1340 and drop, and they only have 1140 in lift. So they're off by 199 there. Huge failure for them, and it gets occluded at a time that closely corresponds to the flat Earth angle. So this distance is extreme, like we're all off a little bit, but it corresponds to our angle and not anything below the horizon or any crazy stuff like that. And so the difference that they get on their what was it? This one, geometric clearance, expected drop. Yeah. No, wait. Yeah, a difference in 40 arc seconds between true position and observer position. And we learned earlier that time of emergence, time that when we see the star, happened within 4 arc seconds of the true position and the refracted position aligning. So we know that this 40 arc second, to even like entertain that as a possible solution, is just ludicrous at this point. So that's where we're at so far with the analysis, and I'll do some things to clean this up and make it more clear. And then there'll be a summary column over here with parameters and everything laid out. And then we can have the data comparisons in a nice tab, or, you know, nice tabs over here where all the positions are represented. But if anyone would like to play with this tab or play with this spreadsheet, the link is here. You're free to make a copy yourself, or well, I guess that'd be the only way you could play with it, huh? So yeah, you're free to make a copy yourself, and how to use it is just change to a peak. All the relevant stars will then be displayed per the peak. And then if you ever want to add something, go to the old data table here, add in the same corresponding order that we did, and everything should automatically update in your drop-down menu relevant to that peak. All right, any questions, comments, or concerns?
I will let someone else go first because I'm polite.
Thank you, Rue. A true gentleman.
There's
In
a
general.
couple people in chat that had questions. I think Chief Squatting Dog.
Oh no, I'm gonna
Triple-
dig through this, and I'm gonna make sure all the file, or I mean everything is like referencing everything correctly. And I'm just gonna look over the basic formula because it kind of looks a little fooey.
Nice. Please do let me know if I have anything off.
Yeah, the
Gotcha.
results can be disgruntling. A lot of people feel the same way, but now that every
No.
method is now included, if you find one that isn't, definitely let us know and we'll add that method.
Yeah. Well, I'll look at this equation here,
Nice.
and then we'll hope that the guy like actually measured correctly to begin with.
Well, the methodology is so easy, even I could do it. So I'm sure he nailed it, because he's much smarter than I am.
Doubtful. I mean, not doubtful, but like not saying
Your
much.
aspersions are noted.
Yeah, that's fine.
Any-
I'll look through it.
Anywho, Ruski, what do you got?
Also,
for us,
why are you
big
using
dog?
the term occlusion when like it refers specifically to orthodontal work? Do you mean to use a different vocab?
I mean to use the time in which something gets occluded by an object.
Occlusion angle.
Brother.
A dental term.
Sure.
Occlusion, the process of
Occlusion
occluding.
is just a dental term. It's a process whereby something is hidden or obscured from prominence or view. The
Something
fact
that
you
occludes.
Googled
No,
it
Yeah.
no,
and just
no.
looked at one definition is absurd.
No, dude, the
I'm looking
celestial
at
theodolite is
the top 7.
the celestial theodolite is actually a dentistry method. So
Yeah.
he actually
Yeah,
just
it's
busted
actually a
us.
known procedure.
I'm just looking here.
Yeah.
Do you mean to know your
Ready.
vocab better before correcting other people's vocab?
I'm just looking at the
All right.
top 7 ones, and that seems to be what it is.
Yeah.
I cannot
Anyway.
believe you didn't look at the second definition that Google lists.
It's
I
all good,
cannot
guys.
believe that.
Guys, we're having a
Molar
all right,
relationship.
all right. We're having a
But you
secondary
should know that without
conversation
Googling.
on some semantics.
Especially when you correct people on it.
Ruhif,
Well, I'll go dig through it.
I have
Yes.
a quick comment if that's okay.
absolutely, Lily. What's up?
Yeah, last time I was saying that Dr. Heffron's method and his experiment are so brilliant in their absolute simplicity in terms of, anyone can do this experiment and see for themselves. But also, I wanted to point out that it's such original thinking. Dr. Heffron, I hope that this catches on in our community, and a lot of us do a lot of original thinking, because I cannot praise the originalness of this thinking enough. I know that you give the credit to God, which is fine. I don't mind doing that also, but you were the channel. And so, but I hope that it inspires our community to come up with such original ideas and thoughts that are brilliant in their simplicity and their originality. So I just wanted to point that out. Thank you. And also, I think, after 3, 4, 5 months of discussing this particular subject, this particular issue, I feel like if people aren't getting it, then it's either like, I don't know, it's a intellectually dishonest, or it's just mental incapacity mentally to really get something that maybe a little bit beyond their level of, what they can comprehend. So, anyways,
Do you
thank
think you have the?
to
Do you
all
think
of
you have the mental?
for
Okay.
spearheading
Do you
this.
think?
Chief's going dog. We're not doing any more of that. So we're not taking any more questions from someone who cherry picks a definition. The second definition says a process whereby something is hidden or obscured from prominence or view. We're not going to have you just troll and waste all of our time.
Thank you, Gally. Ruhif, I think
Well,
you are the
good.
Yes.
next one up.
Cool. So Shane basically refused to do this last week. So Alan, can you steelman the globe position using, say, Pikes Peak as the example?
Which globe position? There's like 7.
Yeah,
You
which
gotta be
one?
specific.
The
My
terrestrial
globe
refraction
position.
one? Yeah, to include
219.
terrestrial refraction and use 219, of course.
Yes. Okay. So
Yes.
okay, so that's 219. And according to the globe again, what angle did the star occlude at according to the globe?
234.
222.
That's
With-
not a
with-
Steelman.
with-
That's not a Steelman
hold on.
either. You're close, Alan. You're close.
Hold on. No, I have the Stellarium position. It occluded at 222 with respect to the observer's position. It occluded
Okay,
at
that's all right.
Did
230.
you adjust?
It occluded. Hold on 1 second. I didn't adjust anything. That's just the angle from the position. There's nothing to adjust.
Yes, there is. Did you adjust for the pressure, his elevation?
What?
Did you adjust for his
Bro.
elevation above sea level?
Bro, Ruhif, I just use the angle that the star was at with its celestial refraction applied. That's all we're doing trig
Right.
based off of. We don't care about the actual
Right, but-
elevation of the mountain. So
You're aware
When-
that Stellarium thinks you're at sea level, right?
are you aware that, oh, so you're saying that there's a different refraction or a correction to that'll be applied there? So it
Yes.
won't be 222. Okay, what is it?
Correct. 219 or 218 and a half.
218 and a half. Okay, well
Yes.
that still doesn't help because I have 219 raw calculated out for distances and elevations too. I did them all. I did the refracted position and I did the I did the terrestrial refracted globe and I did raw globe. I did them all.
Right. So the mountain is 219 and the occlusion happened at 218 and a half according to the globe. That's a match, correct? Half an arc minute.
No, not according to the globe. According to your nonsense superposition, we're using a refracted in a different position entirely. It's entirely a different metric, right? For sure.
Yeah,
The
Rue,
question
hold on
was whether you
1
could
second.
steelman the position change.
No, we've steelmanned it, but listen, Rue, if the refracted position is they added 16 arc minutes of refraction, that's equal to the flat earth angle. So like the different, like with the comparison that you're trying to say is that like the refracted globe position is equal to the flat Earth angle, which if that's your position, you know, touche, I guess. But we're
My
considering
position
the
is
raw
that
as
it's
well.
only half an arc minute error.
hmm
The question was whether you can steel man the position of the globe. No, I don't care about the cell Theo. Can you steel man my position?
You mean your retarded
well,
version,
listen,
warp version of it?
well,
Sure, we
well,
can.
listen,
Sure. Yeah.
listen, Ruhif, I don't understand what you mean when you say, can you steel man it? Because I included all of the angles that you could possibly need and did the calculations based off of whatever those angles happen to be, given terrestrial refraction, given celestial refraction, although I will adjust the elevation for that one. But even using the elevation that you're suggesting of 219,
Do it for
I
Mike's peak.
I have
Mike's
it.
peak.
I have it right here.
Do
You're
you?
off.
None
Yeah,
of
you're
those numbers look
you-
anything right.
you're off for using
Show me Mike's
the
peak.
okay. Pikes Peak,
There you go.
39 Aquarii.
Yep.
Okay.
Cool.
For using 219, we get an elevation of 30 minutes or 30 meters in difference to 800 meters in distance. You guys get 172 meters in elevation, and you're off by 4,000 in distance.
Okay, so question. All right.
Yes.
So my inputs to get 219 are
Mhm.
like the distance, delta height, and terrestrial refraction, and globe drop, obviously, right? They're my inputs.
Mhm.
Right? And then I get 219, and my star occlusion angle is very, very, very close to that, right? 218 and a half. Right?
Mhm.
So does it make sense to you that when I plug in that very, very, very close angle back into that formula to derive a height or a distance, that the number is off? Does that make any sense to you?
Our premise, again, like whether or not it makes sense to you, this is what we're testing here. So when we do that same thing with the true position to the peak, we're somehow able to get our distance, usually within a mile or two, and the elevation of the peak. And you guys are consistently off when you do that.
Okay, so I'll say it again. Let's assume that my star occlusion angle is exactly 219, right? So it's a perfect prediction.
Sure.
If I then go and plug that back in, right? If I go and plug that back into this distance check or height check, does it make sense to you that either the height or the distance would be wrong?
Well, the angle should correspond, or the timing should correspond to what the globe predicts. So the distance that you derive based off of your angle should closely predict where you're at. And it doesn't. The flat Earth angle does.
Right. I'll say it for a third time.
Okay.
If I plug in the distance, the height, the terrestrial refraction, and the drop, right? If I plug in these numbers into a formula to
like I
get
did.
an angle.
Yep. I got
Right?
219 when I did it.
And then then I just assume for the sake of it that my angle that I observe just happened to be perfectly correct.
Yep.
Right?
That's what we're doing here. Yep. With you
If
so
I
far.
then go and reverse engineer a height, if I go then back to that formula to reverse engineer a height or a distance, does it make sense to you that if I plug in that exact perfect angle, that my output would be wrong, like the distance would be off by anything? Does that make sense?
Well, it's going to be a ratio of the known constant, which is the elevation that we're using, and the angle that you get. And we have mutually exclusive angles. So the distance that you get out of that is going to be dependent on your mutually exclusive angle. Do you understand
This is the point of this testing this?
Do you understand why
Like,
we're
aren't we supposed to be testing this?
do you understand why we're doing this? Because for all your griping right now about the refracted position and how it doesn't match, what you don't know is when you take that angle, it doesn't even do it. It wouldn't even do it at 218. It would then be off. So I'll have to adjust it because it's off there too.
Okay.
So yeah. Anyway,
I don't know how many other ways to say it, honestly.
Well,
When
I don't know
you
how.
say that the distance is off by 4,000, right?
Yeah. Yeah.
How is that possible if my prediction is only off by half an arc minute?
Because
my height is off by 172 meters.
Because you're deriving your distance based off of the refracted angle, and we're deriving our distance off of the true position angle of occlusion.
It
Which
doesn't
there
matter
should
what you are doing.
Well, it does, because there should be no geometric relationship between what we're doing and what you're doing. There's no reason why we should be correct and you should be off.
The chief squatting dog just said in the chat, it's because you're doing the formulas wrong. That's what I'm trying to get at. Right? You're not like Stone said yesterday in the stream yesterday, where Stone said you've just you back engineer numbers. I'm fine with that word. That's completely fine with me. But it's just reversing the formula. You're clearly not reversing the formula correctly.
No, we are, because when I first started this, I was actually listen to me, please. When I first started this, the distance derived was exactly back, but that's it would always equal back the angle for flat Earth, because I was using, like, it was circular the way that you're asserting. But if you use just the elevation as the constant, the control, or the difference in elevation, and you use the occlusion angle, which is a dependent variable that comes out of both of our predictions, because you predict a different angle, we predict a different angle. So we're going to get different distances out of that. So now we're seeing the differences in distances and the comparisons, because the globe is built on apparent angles. So I have no problem doing a comparison for what it happens to come out with at 219. You saying it doesn't make sense and we expect a different angle, that's the premise of this. To see which one matches reality.
I'll try and explain it.
Go ahead.
I'll try and explain it generically, right? You know the equation of a line, right? Y equals mx plus b, right?
Sure.
I stick in an x coordinate and I get a y coordinate. If I stick that y coordinate back into that formula, I will get the same x that I put in, right? The formulas are rearrangeable and reversible.
No, that's not, because if we put it, if we put in an angle that doesn't correspond to the occlusion angle, we would get a different distance. That's what I'm saying. When I changed the ratio to get it so that it's not circular, we can get actual differences in predictions where it's not circular, where it doesn't give you the loop back.
What Ruhif is disagreeing with is the actual application of using his refracted angle in practicality to measure things. He wants to subtract and remove the so-called geometric curve and refraction correction that he applied to get it in the first place, right? We already went over this in depth and detail.
So he actually wants to change the observer location. Is that what you're saying, Shane?
Hang on.
I think he wants to, so once he gets his refracted angle, his lower geometric and refracted angle, as soon as you want to measure stuff with it, he wants to straighten that back out and remove that refraction so that he can get a correct elevation and distance.
Yeah, dude, I don't care about any of that, bro. We're doing raw for raw and deriving distances. If you have to do all this like weird stuff, that's a completely separate thing. But I'll pull your thing up and you can go over your spreadsheet. No, we're doing a different. You're strawmanning us, bro.
No, I've done your procedure.
You didn't like the answers you got, so now you're trying to do a different one. That's a post-diction, bro. We're externally testing the internal consistency of your guys' model. When we test it internally consistent, it's pretty much still goes the way of flat Earth. In a couple of cases, it's ambiguous. When we go raw for raw, you guys are off every time. Like this whole disagreement about you're basically, like Shane said, you're basically just disagreeing with the application of it. And if you disagree with that, your contention's noted, but like largely irrelevant. Because if I can find my distance using this method, then everything you're saying about how you disagree is irrelevant. I can find my distance just off of an occlusion angle and a peak.
So can I.
And even arguing over this refracted position nonsense is not even the true Heffron method. You're using a true occlusion time. You're off in fairy tale land using a refracted occlusion time from a different place. That's not the actual original method. It's entertaining your method. We should call it the Ruhiv method. And that's what we're entertaining now with full-on analysis where it still fails, right? Which is why we're arguing it.
Yep. And even doing that, it gives, it's off by 172 and it's off by 4,000. So.
Yeah, because your formula's wrong. Like I said, if I
predict my formula is the same thing that I did for the flat Earth prediction.
Hold on. If I use the distance to predict the angle, and my angle is an incredibly close match to the actual angle, how is it even possible to then reverse engineer that formula to get a distance that's way off? Obviously, your formula's wrong. Obviously.
Let's go over it right now. You can correct
you can't have your refracted triangle and eat it too.
My formula
Right?
is not on. It's just the same thing that we
What?
did with the true position. So for the flat Earth, we're referencing true position at peak. For globe, we're referencing refracted position at the peak.
Right. Do we
Yeah,
want
if-
to waste
if-
everyone's time and reverse engineer my 219 back into a distance? Is that what we want to do?
I did the
I
same
can
thing.
do that, but it'll take me
I
a while.
did the same thing doing the same
clearly
process.
you didn't, because you're off by 4,000. Clearly you didn't.
Okay, well, let's see what we did here. We did E12 plus B19. E12 is standard refraction. That's globe slant.
No
okay,
one's-
one second.
No one's going to watch this, Alan.
I don't care.
Tangent of the radians. That's it right there. Divided by the tangent.
Or which one? Was this one?
Basic angle, globe angle, divided by the tangent. Yeah.
That one?
Wait, no. Whichever one.
I mean, this is
what
what we're
exactly
all.
is your argument? What exactly is your argument?
Me is
You
that it
laid
fits
out?
the globe, which I'll show
right
up 1
here.
second.
Yeah.
Yeah,
The-
that was
the- yeah. Distance times the occlusion angle, bro. Or whatever the refracted angle is. And in your case, you
Yeah,
wanted
where's
to.
times the
the
tangent.
refraction?
Yeah.
Yeah, in your case, you wanted 219, so it goes off of the 219 angle.
Yeah.
Yeah.
Right,
Yeah,
but where do you account
yeah.
for drop and refraction, which are input
We-
into the
In
formula?
219 already.
we
You've
already
used it. You
did.
can't
We-
subtract it back.
We
out.
already did. To get to 219, we had to subtract the drop over distance, which was 213 from the flat Earth prediction.
I mean, I was just here last week, and Ruhef said
Hold on, Toby.
219.
You got
So-
your voice changer on again
Yeah.
for some reason.
Is that Toby?
but yeah,
I never turned it off.
there you go, Toby. You're live.
I was gonna say I was here last week,
Right.
and 219 came from Ruhev.
Yeah,
Yes.
I'm 219 out
Very
of my
insistent
mind.
about it. Yeah.
Yeah, that's why it's in here.
Right.
Like I
but the
incorporated it.
inputs into that formula.
Yeah.
Right, but you know how to rearrange formulas, right?
Yeah, and we're not doing that because it's not circular.
Right.
The flat Earth one gives a different distance for its
Right.
prediction, and so does the globe. Because it's based off of the occlusion angle, Ruhif, not the
Right, so
actual
you're not
input.
doing it.
Dude, the actual input for the angle, right, is the prediction. So it's like based off of the ratio of the elevation and the
218
distance.
and a half.
Stop, don't interrupt me. It's based off of that. It's based off of that ratio, right? It just happens to line up with the refracted peak angle, right? So when we do the same thing that we're doing with the true position, we get a distance that's close to ours and yours is off, and you're saying I'm doing it wrong. And you're saying that why would we expect a different distance? Because we have a different input we're using the angle and deriving it off one of the other known variables to derive the other for comparison. So for one, we use the known elevation difference and the occlusion angle. That gives us whatever distance that would have had to have been to create that angle. Now, when we do the same thing with the angle and the distance to get what the elevation would be, that's why we get things that are different so we can compare based on the actual occlusion angle, which is our predictions. And where was the star's true position when it got occluded? And I figured you guys would want the apparent position when it's occluded. So when we do 219 or 218 or whatever numbers you guys want, that's why they're off. That's why it doesn't reflect that. That's what we're saying when we do this with our method. It's reflecting the geometry of reality because there's no drop over distance to create the angle of triangle that you would need to derive your distance more closely and elevation.
Right now, you're arguing
what
to
is
just
the
subtract that
steel
globe to bring
man?
it back to flat.
Yeah, your argument is
What is the Steelman occlusion angle? What is
Steelman
the
occlu-
Steelman occlusion angle?
It would be 217 raw, 218 if you or 219 if you added refraction terrestrial, but we don't.
219. Right. So that's the Steelman occlusion angle. If I plug
No, that's the
that back
retarded
into
Ruhif
the
method.
formula, you can straw man it all you like, Shane, right?
Well,
But
listen,
if I plug that angle back
Just renamed
into the
it.
formula, I will get the same distance. Because that's how I got my 219, was using
the only way
50.7 kilometers. So I plug it back in, I get 50.7 kilometers back.
what elevation
So
do you
basic.
get? What elevation do you get off of that though? Because
Exactly.
because you
Angle
can't
or delta height.
whatever the elevation would have had to have been to create the mountain peak, because that can't be the same then.
219?
It would be a different elevation, 100%.
Yeah, then you're
I
doing
predict
something
If you have
wrong.
the
219,
same,
and
if you have the same
historic vision
distance
was
and a
218.
different angle, you're gonna have a different elevation, bro. If it's 231, it's a higher elevation. If it's 219, it's a lower elevation. So it's
Yes.
different.
That's why we compare them
Yes,
separately.
it's 219 on a globe.
That's why we compare them separately off of the known variables so that we get the approximation with just the dependent variable, which is the occlusion angle, and the control, which would be the distance or the elevation, respectively. So we're
Right.
not doing
If
it
I
wrong.
calculate 219 as a prediction, yes, you
Mhm.
are, because you're getting an error of 4,000 meters for the globe.
Yeah, that's
I know that
unfortunate.
every step of the way so far, with every formula, it hasn't been the globe is wrong. It's that, oh, we made an error in representing the globe. That's how we ended up with 7 different methods to predict globe drop.
Yeah.
Notice whenever one of them doesn't quite do it, it wasn't, oh, the globe is wrong here. It's, here's a new formula that we need to apply with
Yeah.
a specific
Right.
ratio of new terrestrial refraction that now brings it back. So that's why we have 7 different methods right now, Rohit. So you want to, none of these in
Let's just-
singularity by itself is more consistent, right? We're allowing you to
Let's
pick
just
any of
humbly-
these at any given point that are higher. Okay.
Let's just humbly call me the king. I'm the authority on the globe method. All right, attack my globe method.
Oh, I don't have to. The null hypothesis is my own. I've failed to falsify it. I have no single measurement that from my analysis that shows that there's a mutually exclusive globe proof. I have indistinguishable measurements and measurements where the globe's way off. So when you say
Okay,
attack my
so
globe method,
on my
I
screen
have
now,
no need to do that. I've already done it.
on my screen now is a comparison between the actual globe method, the blue line, and its deviation from prediction, and then the red line is the celestial theodolites prediction versus the flat Earth angle. It's all over. the
Oh, where's
place.
the actual physical occlusion time? I don't see that listed or compared anywhere.
Times?
What's going on with that?
Times are in here. So these are all the times.
From the mountain, right?
UTC. Yep.
For both predictions, right? You're comparing the globe from the mountain and flat Earth from the mountain, right?
Yep. So that's, no, not from the globe doesn't.
No, of
shoot
course
it,
not.
right?
You're doing totally different. You're doing a completely different metric, dude. You're applying the globe from a different position to the observer, and you're applying. It's so retarded.
Yeah, I'm doing the non-strawman version, Shane.
Nah, you're doing
Oh, the
internal.
Rubin retarded method.
Listen,
Let's just agree on what to
listen,
call it, dude.
listen, we don't have to get insulting, but what you're doing, Rue, is an internal consistency check. We're doing an internal consistency check with our method and an external one, and we're giving results that show that the Earth is not a globe. So when you're doing an internal consistency and you're like, look, when I derive it based off of these variables, it comes back to the same distance. That's expected. Like you're doing a different thing and then saying that we're strawmanning the globe, but I told you we're testing it externally and internally using the occlusion method. If you don't agree with that, that's fine. If you say that's a strawman of the globe, that's fine. But you're referencing an internal consistency check to refute our data and then say attack my globe position. Bro, the whole purpose of what we did has refuted your internal consistency check. But go ahead.
Hold on. So this column here, so this set of values here in particular, are the deviations from prediction for Pike's Peak. You'll see they're all less than an arc minute. That's amazing, quite honestly. The celestial theodolite, doing it your way, testing your method, it's always about 2.5, 3 arc minutes off. All right. You go down further. What do you got? Cheyenne and Blodgett Peak here. They're off by 4 and 5 arc minutes. What's this one? North Peak Greenhorn off by 14 arc minutes. Jesse's Blinn Mountain off by like 15 arc minutes. Your method.
But you're literally doing
does not
apples and
give
oranges.
results.
Right? You're doing
No,
flat
this is
Earth
your
from
method.
the peak to the star, and you're doing globe Earth
This is your
from a
method.
different position using a refraction to
Yeah,
a
you're
mountain peak.
using
No,
a different
it's a completely
position.
different method. You have a different metric. You have a different
219
occlusion
zero-
time. You're pretending that true time isn't the actual time. And for the
You
globe,
have
you're not
a
comparing
solarium
the same
angle of
occlusion.
219,
You
bro.
have
You have
different-
219.
You have different occlusion times. What are you even comparing? This is retarded, dude.
That red line is your method.
You're not
It's
comparing
rubbish.
to anything. You're comparing it to a completely different method, which is looking at a mountain to gauge its elevation, a known process since 300 years ago, which is
He
unrelated.
seems to not be
This red
Completely
line
to this-
compares. The red line
Roof,
compares
as
the
a
celestial
house
Ruhe.
insider, can I ask a
angle
question for some
to
clarity? Can I get some
Flat Earth
clarity,
angle.
Roof?
Hey, Roof, how
Yeah.
are you? Are you still using the measurements of the occlusion timings?
Yes.
Okay, can you show me?
Occlusions here. Boom. Goes in here. Oh, which freaking formulas do I got to unhide?
What are the
No,
positions?
but like, how is it in your chart?
Yeah, hold on. I got to figure out where those times are.
Because Shane says you're
He's
using
using
apples and
different
oranges, but
times.
it sounds like you're basically looking at the wrong metric.
He's comparing two completely different
Globe
metrics.
stuff. Hold
He's
on.
comparing true occlusion with flat to refracted occlusion observed from Heffron's house to the mountain. Completely
Yeah,
irrelevant.
he's
to the
using
method
a
in
different
entirety.
position of where the observer is. Our method is using the peak to the
How
star.
is, so then, how is the occlusion even going to be relevant if you're not even in the same position?
Here we go.
Exactly.
So these columns
He's
here
not gonna answer
work
that.
out the
Ruhif,
hang
you
on.
were asked a question.
These
What
columns
is
here.
He seems to be
Yeah, I'm trying to
ignoring
answer
those
the first
things.
question. The question was, am I using the occlusion time? The answer is yes.
Okay, and we got past
So
that.
this
You're
takes
showing
me
me here, but then now I'm being told that you're not even using the same position. If you're not at the same position, how are you using the occlusion timing from the position where it was actually physically observed?
All right. So there are two things happening, right? Two things happening in this graph. This one is showing the deviation from prediction. Why are you laughing?
Because he just asked you a question and you glanced past it like 3 times, bro.
Well,
Let
I'm
him try.
answering it.
Let's give him some time. Let's see if he can cook something.
Right. So this red line is showing the deviation from the predicted angle, right? So you move the observer to the peak, turn off the atmosphere, get the star angle, and then you compare that to the flat Earth angle, right? That's this red line.
So you're
It's
not using
all over the place.
observations?
Bro,
These are observations.
Ruhif, we don't dispute the optical angle difference. That's not our argument at all. We don't care about that at all,
I
bro.
understand that.
We're deriving our distances and elevations based off of this. You're doing it like, bro, you're not like oh man.
You're not using the
That's
observation.
that's crazy, bro.
And
Ruhif,
now he's
Ruhif,
just shitting everywhere. Yeah.
Ruhif,
Yes,
Ruhif.
I am.
Yes, you
Yes,
are,
I am
bro.
using the observation.
Listen, I can not in the correct way, bro.
Yes,
I can
right.
derive my distance and location. You can't. You're not even doing the same thing. You're
Isn't
doing
it?
you're doing angular comparisons. That's not what we're doing. That's not at all what we're doing. That hasn't been the
Oh,
method.
okay. We'll
That
convert
has
them to distance. That's fine.
That's why I
yeah.
like the different
That's
name for it. It keeps it keeps
dude.
it clear and succinctly different, right? No
Ruhif,
one
if
gets
you
confused.
know
when
what
it's
you're
called
doing,
Alright,
dude.
versus
He
okay.
knows
original.
exactly what
Dude,
he's doing.
I know, man. We've been on this
Let's move
for
on.
a hot
Yeah.
minute.
Yeah.
All right, Ruhif, it's been a pleasure, man. I'm gonna have to go ahead and take some audience questions here, and we'll come back to you next week or something. That's insane, bro, that you just did that all for an angular comparison. To sit here with your chest up, come in here streaming over my stream, talking about fucking angular comparison when you didn't use the right angle, you did it wrong. Yeah, no shit, because I used your refracted angle, and that's why it gives a different distance, bro.
Dude,
That's crazy. Like,
just to summarize, the globe,
dude, just so
the
everyone's
globe was
clear
wrong
here.
every step of the way.
Yeah, just
right?
so everyone's clear here,
Then-
what just happened? Like Shane just said, every step of the way, the globe is wrong. To only obfuscate and turn it around into optical comparisons, which is not the method at all. This whole spreadsheet about deriving distances and elevations, that just did that for no reason. It means nothing, has no physical implication. I can get my location from a occlusion time and an angle. This man sat here and said, I can do the same. He didn't do the same. His graph is not even related to what we're doing. He absolutely can't do the same. This is what it looks like when the globe tries to do the same. It's off. It's not the same. That's preposterous, bro. Thanks for coming on, Rue. I really
Dude, wrong every step of the way, and then at the end, change it all entirely.
Dude. Anyway,
Hey.
are there any questions from the audience, boys? And what's up, Beast?
Wait, Alan, I would like to respond to Ruhif afterwards.
Go ahead, man.
Go ahead.
19, and then the star occlusion also happens at 219. How is it even possible
but okay.
when I try to reverse engineer a distance that it's not what I input?
Okay. Ruhif.
Right.
Do you remember when we first brought up the celestial theodolite method? Do you remember what you said? about how the true geometric angle from the peak to the star matches a flat Earth baseline, and you were like, "Oh, that's just a cosmic coincidence." Remember that?
Yes.
Where are your occlusion angles from the peak to the star in your spreadsheet?
That's the red line. See how the Pikes Peak one is?
Oh,
it's
so
not great,
that's
but it's
our method,
2 or
right?
3 arc minutes off. Yeah, the red line is
Right.
your
So,
method, and it's about 2 or 3
uh-huh.
arc minutes off of Pikes Peak. Like I said, that was a bit of a coincidence. And like we said, Mount Rosa, because of its combination of distance and delta height, is going to be very close to being a good method, a good result. But the rest is rubbish. Look at Cheyenne and Blodgett and North Peak and Blinn Mountain. They're all rubbish.
Yeah, but
doesn't
Ruhif, you
work.
do realize the method itself, right? Stellarium does not know how far away you are from the mountain peak. You know that,
Yep,
right?
fine.
Okay. So if you were to derive the distance with 219 and your elevation, what angle would that be?
Yeah, I can
Would
do
it
that.
be 219 or would it be 231 or would it be a different
219,
angle
the
and different
occlusion
height,
height.
different distance?
No, yeah, you misspoke there.
You're talking about sort of
It would
reverse
be
engineering a globe number?
it would be distance. There's no globe number, bro. There's a fucking elevation angle for a mountain peak. That's our constant between the two. And there's two angles of comparison. When you do the angle versus the elevation for 219, you get a distance that's off by fourth. Hang on one second. Let me change it back to Pikes Peak. You get a
Yeah,
distance
don't
that's
hold me
off
for
by
shit
four.
about
Shh,
Alan.
dude. Okay, dude. It literally can't give the same.
It's two different angles.
I'll say it
It can if you
for
change
last
it.
time.
Like that's
If,
like
if I use a distance to get an angle and then I put that angle back in, I will get the same distance spat out. Like,
yeah.
it's basic.
That's why we're not doing that, because that's circular. We
Right.
reference both of them from a different perspective. So for the one we reference the difference in mountain elevation to the occlusion angle, and then for the other one we reference the distance to the occlusion angle to get the elevation, and we compare both differences. We don't do them the same, because then you would derive it exactly back to the same. That's like dude, when you say
That's what he wants.
no, it's not a
Yeah.
straw man, bro. It's literally two different fucking things based off of the one that should have no geometric relationship, and the other one should give you the exact distance based on the globe angle. That's not a fucking straw man. That's externally and internally
Okay, so
testing your
steel man
guys'
position
method.
again.
The position is to use the
Steel
refracted
man,
position.
the globe position.
The globe position is to use the refracted position to derive the elevation and distances, the same way that we did the flat Earth for the comparison. Anything other than that would be to straw man the globe. There's no other position I
Okay,
could
so
use.
the steel man is a 219 prediction and a 218.5 observation.
Changing
If
the
I
whole method.
reverse
Got it.
engineer a distance from that, I'm going to get very close to 50.7 kilometers.
All right, Ruhif, tune into my stream real quick. Let's take a gandy here and make sure there's no straw manning going on here. So you want 219, right?
Yep.
Okay. If we do distance times the tangent of the occlusion angle, we get I'm sorry, that's for elevation. We get an elevation of 192 meters. Okay, the actual elevation was.
Right, but why are you not
Hold
reverse
on,
engineering it?
hold
Why
on,
are you not
hold on.
back engineering it?
Because that would just give us the same thing. It would be circular. And I do the same thing for flat Earth, so we get two separate predictions per
Jesus.
per thing. What do you mean, Jesus, dude? And then so for distance, we do the distance times the tangent, or over the tangent of the occlusion angle. So we have two independent things based off of the occlusion angle and the known variable, so we can compare how each model fares to deriving it in the way that you want to. This is the best way to see which method is right, because if you do yours, which is derived off of optics, it's going to be internally consistent. It's not going to be different if you don't change one of the other variables. That's why we do it that way. If you disagree with that,
just straw man it every day, all day.
no, that's not a dude. If it's a straw man, then why is the distance close, but it's not what it is? Like, it's not a straw man. They're both like, there's instances where flat Earth is off, but then globe gets close too. Like for Jesse's data and stuff. It's not a fucking straw man, bro. And when I get into the apparent refracted position with spherical geometry, it's even closer. It's within a mile. So you're going to call that a fucking straw man if I could find my position using the refracted position or the true position with the peak? That's not a straw man, dog. If I can accurately find my location on the graticule using occlusion timing and one known variable of the mountain peak, that's not a straw man. That's dead on fucking maths accurate. You're refuting nothing and doing a different methodology, and it's frustrating.
All right. I will say it one more time, and then I'm just going to drop, right? If my prediction uses 50.7 kilometers and gives me 219, then my observation in reality gives me very, very close to
Bro,
219.
just drop. Nobody wants to hear you anymore.
I'll start again, bro. All right.
No, you're actually not going to start again, dude. You're going to go fuck off. That's insane.
Or he was
All
not
I did was
answering any of
detract
these
entirely
questions.
from the point of the method. Yeah,
So-
let's not use true occlusion times and deviate
Kept
everyone entirely to
obfuscating,
a
going back.
refracted.
No. So listen, so pay attention, Globe lads. The point here, right? If you're going to refute this based off of occlusion angles, you have to be able to find your distance. Remember the argument of how come I can use the stars to find my location? How come blah, 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 sky, I can globe, right? Well, we're doing the same thing with occlusion angles using plane trig and also comparing what the globe would do for their physical elevation to the mountain. They should be closer. We should be off. It's always they're off, or it becomes indistinguishable in the predictions where their refracted angle is equal to the position, the true position at the mountain peak, which makes it indistinguishable. They're never better than us in prediction.
Did you guys kick Ruhiv?
Sure did.
He was just debating you guys.
If that's
Okay.
what quote from Ruhiv. I'm going to repeat this thing I said for the 30th time, and then I'm going to restart in the middle of it. Like, nah, we're good. While simultaneously not acknowledging the method or doing anything and saying that we're doing it wrong when there's no possible way that it could be wrong if you do it the internally consistent way. If you do it a way that compares it, you can see the distinction between the two. So his whole point was to come here and obfuscate, not do the method, not acknowledge it, say that we're straw manning the globe while simultaneously providing every possible way in methodology to represent the globe, to be fair to it, to represent it to our actual methodology, which provides our distance and elevation to a mountain peak. Something that they can't do. And he
Yeah,
talks
they-
about it.
Toby-
Sorry. go
Toby
ahead.
asked him direct questions. He did not answer those. Instead, he went back to his chart, his graph, said red line,
Oh.
blue line. He did not answer anything Toby asked him.
And his
Yeah,
chart,
Toby
Virtue
pointed him out that
jerking
he's
on
not even
behalf of
using the same.
Ruhiv.
I would want to
Yeah, that
reiterate
was
one thing I
ridiculous.
brought up last week that I think is just as relevant now is like, where were these objections months ago when you guys were planning this methodology out?
dude, as soon as we started quantifying it, then it became rubbish. First, it was just an interesting coincidence. Mike bought his house 11 years ago, and he's a flat Earth plant, and it just so happens to be flat where he lives, and all this ridiculousness, right? And then we started doing it at other places. Jesse went out and did it. We started looking at the data, comparing it. Methodology solid. The occlusion timings happen within 4 arc minutes of intersecting with the peak, and then we get into we get the ability to analyze the actual differences and how much refraction impacts it. We see it's equal to, double, or tripling the amount of expected drop, completely compensating. The refracted angle is giving accurate distances and positions when it's close to the true position of the peak, the actual elevation. Like Mike's position's completely substantiated through all of this. And the only thing we're getting back in return is like my angular comparison. And how come when I use 2 known variables of the triangle to get it back to the distance, it would work out? Because what he didn't tell you about that, to get the 250 distance, to get the difference elevation, he has to use the actual elevation and not the drop over distance one to get it to if he would to get it to come back to it, which he can't do. So that's why he didn't show it. So this,
I mean,
so this whole
Very
thing,
dishonest.
dude, like,
like quote from the people that were like, if I was ever given evidence of a flat Earth, I would you know, I would admit it and all this stuff. Nah, dog, you're just straight walking away from it. We have repeatable measurements that anybody could do. We have spreadsheet analysis on all the comparisons, all the angles you could ever possibly want. And the only thing that seems to be consistent is when it's a flat Earth angle. And even when you get into the spherical trig analysis using the graticule, which gets a little complicated, but even in using that with the flat Earth angle, it comes out to be it comes out to be the accurate defining measurement, and there should be no relationship. It should be dead wrong.
Audience
He
questions?
followed
I
every
got a couple.
objection.
If you want,
He followed
audience
every
questions,
objection.
can move on from
Yeah. So
computation if you want.
yeah, good call. So if there's any audience questions, if anyone has any actual questions about the methodology, the differences, we're happy to take them.
John just said he has a question.
Yeah, I got three audience questions. So the first one is, why are you using Google Sheets for trig functions? Google Sheets is so cancer. This is literally the worst format to check work. I'm an accountant. I wouldn't use Excel for trig, let alone Google Sheets. So that's the first question.
Well, get out your fanciest your fanciest TI-86 calculator out. Do the same do the same arctang functions that I did, and see if you get a different, more better result than what I got, and let me know how that goes. And show me in your fancy spreadsheet the deviation between the two. And if you use Google Sheets, it's unacceptable. Next question.
Yeah,
I hear you, John.
We'll get you in for the 10 minutes you were asking for after the three audience
Yeah.
questions.
Okay.
All right. The next question was, ask them why the southern stars don't rotate around Polaris, and how do you navigate using the stars in the south, considering the stars aren't where they are on a flat Earth? How the F do we never get in the south using the stars?
Well, the apparent that has nothing to do with the methodology, but the apparent positions of the stars is what was used, and they used to do run line sailing, which is they would have checkpoints where they would go to a position, adjust their bearing, go to that other position, adjust their bearing again. You could look up the Perry-Reese map. That's the baseline for run line sailing, and that was run line sailing before they had latitude and longitude. So when you look up the what run line means now in modernity, they've redefined it to mean a straight line over curved lines or whatever. But they were doing this before they even had latitude and longitude. So the idea that a run line is mutually exclusive to going over a curved line is retarded. It's been redefined, but that's how they used to navigate. None of them were globe lads. Back in the 1400s, the Chinese had an expedition where they were doing the run line bearing sailing using the Perry-Reese map. They sailed all around the world, discovered a whole bunch of stuff. Even Magellan going through the strait, he wasn't the first person to go through it. The Chinese were, and then he even made references to stuff that the Chinese were talking about in regards to other locations. So there's a history of that, and they were all geocentric flat earthers, by the way. And then up to the 1800s, the Buddhist monks and Shintoists over in Japan were geocentric flat earthers, and there was a working geocentric flat earth model at the Tokyo World Fair in the late 1800s that was on display for a number of years, that basically had a central axis, and then it had 4 azimuthal domes positioned in a circle on a disk, and then above it on the axle was little planets, like little spheres, little copper spheres and stones and stuff that would be shiny, and those would rotate around, and then you would see them displayed in the azimuthal grids, like through the mirrors. And then the celestial disk that's rotating on top over the axis would go up and down, and that would change in elevation to how they would see them on the ground. And so that the way that they conceptualized it back in the day and justified it as flat earth geocentrists for navigation was that each continent had their own hemispherical dome that the heavens were perceived under.
I couldn't understand what that person said, but there's one more question. This is from Morningstar, and I think at the start, Chief Squatting Dog. Why the choice of the word occlusion rather than the word occultation, where the opinion in the chat was that occultation would be the more appropriate word, a term used in astronomy? Why the choice of the word occlusion rather than occultation?
Oh, I don't care, and I just work here.
Yeah, I think the terms are equivalent in this specific example. All right, those are the 3 questions. John had said he had a couple questions that he wanted to ask. He said he wanted a couple minutes to talk to you guys, so I'll hand it over then.
Go
That's all
ahead,
I have.
John.
Thanks. Yeah, I just upload once again the screenshot that I posted a couple times, but just so it's right there. This is ostensibly a spreadsheet. I give you the link to it, but there's no calculations here. It's just a compilation of results that I think there will be no disagreement on. And I wanted to just limit the number of words. I think one of the problems is when we start talking about all the different peaks and all the calculations, it gets complicated. So I want to limit my attention to the original observation of 39 Aquarii being occluded by Pike's Peak on 31 January. I think that's what Ruhith was talking about as well. And if you look at the thing that I just posted there, I think we all agree that the geometric elevation, so first is flat Earth calculated values, the geometric elevation angle of Pike's Peak from Heffron's house is I get 2 degrees 31.4 arc minutes. You might disagree with a few tenths of that arc minute, but I think, do we agree with that number?
Yep.
Yeah, and then if you do the same thing, putting in globe drop, you get the geometric elevation angle is calculated on the globe to be 2 degrees 17.7 arc minutes. I think we agree with that. There's a tiny little atmospheric refraction effect between the peak and Heffron's house. I calculate that to be about 1.7 arc minutes. Your mileage may vary, but I end up, and I think everybody basically agrees that the visual elevation that we calculate with standard atmospheric refraction from Heffron's house is 2 degrees. I get 19.4. Once again, you might disagree a few tenths of an arc minute.
Well,
Fair enough with all that?
I would like to introduce a objection entirely, though, to the refraction correction, because
Okay.
again, the occlusion happens on the other side of the mountain. So the refraction between you and the peak are
Okay,
irrelevant
fair enough.
when
Fair
you no
enough.
longer
But
see the star. That's all that matters. But yes, I also include refraction as mine for a comparison too. But continue.
Yeah, okay, fair enough. I don't, as far as that goes, I think you can forget, don't even have to include it. It doesn't change the bottom line.
Well, it does in other
and then
measurements
also-
though, because it's a ratio of the
Okay.
distance for how much it impacts it. So it doesn't seem like much in this measurement, but it actually affects it, to, varying degrees depending on the ratio of the distance and elevation. So anyway, continue.
Okay, I just want to stick with this one observation. And the globe, the angular displacement, right? This is a number that I know everybody's familiar with. When you go 50.6 kilometers around a 40,000 kilometer circumference globe, that amounts to going up almost half a degree, 27.3 arc minutes. And all
Mhm.
objects in the sky that you move toward rise by 27.3 arc minutes. I think you understand that too, Alan. Fair enough?
Mm-hmm.
On the globe.
Yes.
Okay, and then turning to values from stellarium, for which you have to input pressures and temperatures at the observation point, at least for visual things. Stellarium says that at the time that Mike Heffron observed the occlusion, the geometric elevation angle of the star from his house, from where he did the observation, was 2 degrees 5.6 arc minutes. I think that number isn't referenced very often because it doesn't figure in anybody's calculations.
well,
but I
if-
put it here
It's
because it is
irrelevant.
going to be kind of important.
Yeah, I put
Sorry?
it in. No, well, I put it in for a comparison to the 360 times the distance relationship to track
Right.
true prediction. What's it called? Predictions, and then also if we did true position to true position for observer, you guys would never be on, like it would never be close. So it wouldn't really be fair to do that to you guys. To do the 206.
Okay. But I think you're saying pretty much what I'm going to do here in a couple of lines as well. Stellarium also says that the visual elevation of the star at the time that Mike saw it from his house being occluded by the peak was 2 degrees 18.8 32.8 arc minutes is what I get. Once again, that may be off by a few tenths of an arc minute, but that's basically what I see. I think you agree with that too.
Yeah,
And
so I
then
got
if you ask
222,
Steller,
but
yeah, go ahead.
I got 222,
Oh,
but
I don't
Ruhav
think
said
so.
my refraction thing was off because I didn't have the barometric
I
pressure
think
thing,
that's
right?
right.
Yeah. So I don't disagree with
I did
218.
that too at first, so I think you made the same mistake that I did originally,
I
not
sure did.
putting in the pressure and everything.
Yeah.
Anyway, then if you go to Pike's Peak, as you well know, the Pike's Peak stellarium says the geometric elevation angle of the star is 2 degrees, 32.9 arc minutes at that time. And the visual elevation angle of the star, where it's actually seen, is 2 degrees, 42.2 arc minutes, according to stellarium. So just those numbers. And I just pointed out, I think the thing that you mentioned there, that 232.9 is the 256 from Heffron's house plus the globe, well, plus an amount that happens to be, maybe by coincidence, equal to the globe curvature between Heffron's house and
Which one are you talking
Pike's
about?
Peak.
Which one was the difference? The refraction
The fact
correction
that the
plus
geometric, the fact that
the raw?
no refraction correction. The geometric angle of the star from Pike's Peak is exactly 27.3 arc minutes higher than it is from Heffron's house, which coincidentally enough, I don't think it's a coincidence, but it is equal to the globe curvature between Heffron's house and the peak. That is a fact, whether you think it's a coincidence or not.
No, I don't
So there's
doubt it.
that.
I've seen some interesting coincidences with the 360 relationship too, because there's one I think for the true position from observer location. If you do 360 times the distance for this one, I think it's like a couple arc minutes off in distance or in position for the true position of it. But for other mountains, it's like a degree off, so it kind of varies with that. So it'll be interesting to track that per mountain peak.
Yeah. So that's the data, and I think, as I say, we basically agree on the data. So the first question is, why doesn't it matter that the visual elevation of the star at the time that it was visually at the same place as the peak, as you know, in other words, the time when it was occluded by the peak, that's when it is visually at that same place. Why doesn't it matter that that visual elevation agrees very well with the globe calculated visual elevation of the peak, and not at all with the flat Earth calculated value for that elevation?
That's a great question. And the
Completely
reason
irrelevant.
for that is because we're referencing the true position alignment because the star has a light source, so-called, right? And that's calculated by using its position of where it once was on the first point of Aries with respect to 15 degrees per hour. So when we're comparing what the intersection angle between what the physical intersection angle would have to be between the so-called light source and the apparent position. That's why we make the comparison to the position that we don't even see, because we have to we're going for what the light source would be, right? So that's why there's a difference there. And when we derive our distance based off of that, there should not be any geometric relationship with the occlusion timing, because there shouldn't be a physical peak there at that elevation to cause that angle of occlusion if the Earth is flat versus if it's globe. So that's why we take that's why there's two things are we derive them off of two separate things. And the globe, of course, is built off of the apparent position. So when we do apparent position at occlusion timing, we get elevations that are sometimes close, depending on if the refraction was enough to make the apparent position equal to the true position at the peak.
Okay, so I know I do understand why your value is different than this, because you have a completely different method. That's fine, but that wasn't really my question. My question is, why does it not matter to you that the visual elevation of the star at the time that it was observed from the place that it was observed is the same as the globe calculated visual elevation of the peak that is occluding it at that time?
Oh, yeah, because
Why doesn't that matter to you?
yeah, so that's part of our
Physical,
premise. Yeah,
John.
that's part of our premise that the optical that the drop, right, that the way it looks is due to optics. It's not due to physical Earth curvature. With the method that we do that you referenced as being a completely different method or whatever, it's not. It's an external test of the internal consistent method that's based on the optic angle that you would produce. So that's why.
Yeah, once again, I think you're explaining to me why your method gives a different value, but it doesn't actually address the question of why it doesn't concern you that Stellarium reports that when Mike Heffron saw that star at the same place as the peak, it was at the angle that the globe Earth calculates for that peak and not at all at the angle that the flat Earth calculates. That should
He's saying that's to be expected.
And John, so check this out, my man. So the refracted process and occlusion process, right? The refracted position can't be what does the occlusion. So think about this. At the same time, simultaneously as your globe angle is being refracted or being occluded by a physical process that is not due to the apparent mountain or the apparent position of the star, because those two things could never occlude one another. When we reference the actual thing that would be the thing that does the occluding, we get the actual distance, right? So your optical angle
once again,
is
I
irrelevant.
understand your method.
So if you say I understand your method again and then ask why it's not a factor, then that's not a real question. And how are you going to start trying to talk over me in the middle of me explaining to you why we don't care? Like, just actually listen instead of waiting to repeat the same question over and again. We don't care.
We're differentiating that, right?
Because we're referencing when there has to be a physical occlusion, what elevation would have to be to do that physical occluding. The optical angle matters not to us.
Right, if it did.
This is the last question. And that's just this, that if
He
the
doesn't
Earth
understand
is
why.
flat, how can the geometric direction to the star, the actual geometric direction to the star from Heffron's house, where he was actually observing it, is 27.3 arc minutes less than the geometric direction to the star from the top of Pikes Peak? If you draw yourself a little picture like this, I'll put this last screenshot up. I ask you to look at those two. One is the direction to the star. That's the geometric direction to the star. Oh, sorry. That's the geometric direction to the star from Heffron's house. That's the 2.093 degree thing. That's the actual literal direction to the star from Heffron's house. And then that other one there, the 2.548, that's the geometric direction to the star from the top of Pikes Peak. How can those two things point in completely different directions? They can't point to the same thing. They're pointing in different directions. How does that work?
I have no idea what you're talking
I
about.
don't even know what he's asking. No.
I'm
Sure,
looking
but
at
all I know is that
I'm looking at your graph. What are you talking about, bro? Here's the thing, John. Here's the thing. Here's the thing,
let
bro.
me just explain.
No. Let me just explain this real quick. Suppose I have no idea where I'm at, and all I have is an angle that the star wasn't visible at, and an elevation. I can derive my distance based off of that if I use the angle that closely corresponds to the flat Earth. If I use the angle that the flat Earth predicts would be the angle that closely derives my distance every time. So that's all I care about. I have no idea what your objection is, and honestly,
well, dude, what he's not differentiating is we're trying to do physical versus optical, and he's trying to confirm it by measuring optics and saying, look, it appears to do the thing we're saying it does. And we're saying no, in physical actual reality, when we subtract the geometric Earth curve from these occlusion timings using the physical timing, the actual timing from the mountain, then it's failing, right? That's what we're saying. So they're saying, oh, we realize that, so we'll never talk about that, and we'll talk about everything else.
Oh, yeah, the classic switch and bait. So listen, that wraps up this week's episode of Celestial Theodolite.
Do I get one more?
No.
You didn't understand my drawing, do I? get a
No,
chance to at
it's
least. No, I don't
a
even get that chance.
no.
Okay, that's
Understand it.
that's helpful.
Yeah, no, we get it. It's another optical comparison. So like when Ruhiv came through and was like, "Yo, my does the same thing," and then he just referenced my optics graph, and Toby was like, "Yo, where are you doing distances and comparisons on occlusion angles?" And he was like, "I have to go," or whatever. And then I kicked him out because like you're just preposterous. And then you came through and basically restated the same thing, and then even went as far as to say, "I don't understand. Let me restate it again." Did that 3 times, still didn't produce any distances or elevation predictions. All right, boys. So to quickly recap here, we are on week 14. There is no globular derivations provided thus far that give a distance or elevation to the peak that correspond to what the globe actually predicts when tested internally and externally using any angle that they would prefer. All right. The spreadsheet will continue to be developed.
Stellarium gives you, right?
Except for the ones that Stellarium
It
gives
gives
you.
you the real
What do you
observed
think?
angle and
What do you
distance.
think that contribution added to the conversation, Daza? Because as we just went through all the Stellarium angles, and at the time of occlusion, when we derive elevation and distance, none of them corresponded to what would the globe would predict for the physical elevation of the mountain. So when you come through and just say that again, like you just like I'm just the chime in fairy, you're just gonna come in and drop a great idea on us, dog. Straight like Daza, great contribution to the convo, bro. It.
Well-
Except for when Stellarium makes the prediction, it doesn't. We're looking at a spreadsheet right here where it's all Stellariumed out. Look, Stellarium off by 125, off by 3,000 distance. Flat Earth off by 36, off by 860. Which one of those values is closer? Spoiler, it's not the refracted globe from Stellarium. Like, why would you come in, say that, and then just like that's your contribution to it? Like, what is the purpose here? What kind of level of like?
Yeah, he's gone already.
Good.
So far, the
The
purpose.
presentation to try to sneak in when someone says they're wrapping up the presentation, they're ending it, and ask a question. That's not exactly bad faith to say, "Hey, we're not taking questions right now." In fact, Alan answering the question is good faith.
Yeah, and for them, like, to say the refraction stuff, well, even if you could see on there, like, even the refracted globe does not match, as he mentioned. So even just turning on refraction doesn't necessarily fix it, right, Alan?
Not even at all. So like
Yeah, and
a
they
couple.
technically shouldn't even have that anyway.
Yeah,
Alan,
and
do you have time for one more audience question, or are you fully wrapping up?
I'm fully wrapped, dude. I'm trying to get out of here, dog. Ugh.
Sure.
I'm tired. I'm tired.
Can I make a comment?
You sure
Whenever
can,
it was
Taylor.
closer to the globe on Jesse's prediction angle, it was only like a few seconds difference between each model. Like if you're
Dude.
sitting there seeing when the star occludes, it's like a few seconds difference between the globe and the Earth. So they're almost indistinguishable.
Yeah, so let's take a quick Gandy at that. So for Jesse's one, the distance was 22,000 meters, elevation difference of 629. And then the true position of the star at the peak was 1 degree 9 arc minutes, and the refracted position at the star was 1 degree 28 arc minutes. So they actually exceeded the elevation of the peak prediction, which when we go through the refraction correction, because they expected 38 meters in drop, and then they have 133 meters in lift. So when you get to that, it's like, it becomes indistinguishable. And like I was saying, with the parameters I set, if you're not better by 60 in elevation or a mile in distance, or 1,600 meters in distance, then it's indistinguishable. So the globe is never better than flat Earth. It becomes indistinguishable at a certain ratio of refraction versus true position. When they're the same, they're indistinguishable. I mean, it doesn't take a super genius to understand that that's logically, that makes sense. You're like, okay, yeah, you can't use that as a comparison. If they're the same and you're comparing apparent versus true at peak, and those two positions are the same, you're not going to come up with a result that's going to falsify one position or the other. So, and then with that, the occlusion clearance there happened within 2 arc minutes. So within 2 arc minutes of the true position intersecting the peak with respect to its apparent position, they were occluded. So method validated.
Well,
I got a question. You guys got time?
whole globe defense seems to be to not talk about that specifically and bring it all back to optics like they did 16 presentations ago. So I'm just pointing
Yeah.
that out.
Yeah.
But
What
we
do
still
you?
entertain it.
Yeah. What do you got, QZ? We'll go ahead and wrap up on that.
So would you say so? Just like to put it simply, would you say flat Earth? And what you guys are claiming the occlusion should happen on the flat Earth? Um, is it later or earlier than the globe claims?
So if it's an occlusion, the occlusion will happen earlier than what the globe predicts because the elevation's physically higher. So the star doesn't have to get as low in the horizon to be physically intersected. And then for an emergence, when the star is rising, uh, the globe would predict that the star would be visible sooner because they're saying that there's no relationship between the true position and the apparent position in terms of the observer being able to see it because they invoke refraction as a 1-to-1 ratio. So they should see it sooner. But what we just observed here through Jesse's measurement is that the star wasn't actually observed until it was within 2 arc seconds of the mountain peak. So in other words, to get like an actual globe measurement, they would have to have an occlusion angle that happens at a later time. And then that would make our distance be off, and that would give them a distance that's more on because that angle would correspond to the proper elevation of the peak that actually did the occluding. So even though they invoke as much refraction as they want, we can now compare the positions of the occlusion timing and like where it was, what the difference was. We can get a clearance tolerance. We can get how much lift there was. We can figure out how exactly they're cooking the books, so to speak.
Yeah, I just wanted to clear up on my point. So if you're watching the star get occluded by the mountain, in the times where they were indistinguishable or where it was closer to globe measurements, it was like a 2 seconds difference. It's like, okay, the star is being occluded. Okay, now would be flat Earth, and now would be the globe. Like, it's so crazy to have like within a few seconds occlusion difference, and that be like the proof of the globe. Ideally, you want there to be a big gap so there's no like room for error, that an error margin that's so like high that you can't even like have a significant set
Yeah.
of data to distinguish.
No, that's exactly why Mike went to, was using North Peak and stuff because that's the furthest one to get the most extremes on the most extreme differences on what each model would predict. You wouldn't go to the spot where they would become indistinguishable, right? But yeah, if there's nothing else, we'll wrap up on that. Call it a night, lads.
Oh,
Such
John, can you guys hear John?
nah.
So if you ignore every metric of the method you profess to love so much, then yeah, I guess what you're saying makes sense in context, right? No, it's okay. I'm done, John. Nobody cares. See you later, buddy.
Yeah, glad I didn't turn his volume up to hear that. I just assumed he was repeating what he already said.
He did, of course. He just wants to repeat it slowly
He
to
said
draw an
absolutely
emotional
nothing.
reaction.
Yeah, you can
Class-
finish up your wrap up, Alan. I don't
classic-
think there's any other
classic-
audience
classic-
questions.
Classic
I have a-
John. All right, who has the question? Who was it?
Yeah, you can't distinguish between the two models using that method though.
I have a question.
You send it.
So does this, all right, let's just pretend like we're not using angles to stars really close to mountains. Like let's use stars close to your zenith or like at 45 degrees. Does that match the flat Earth or whatever you think it would have to be? I don't even know if it's not anymore.
So the reason we're able to derive a distance is because we have an elevation to compare it to. What you just asked about will be part of a secondary analysis that is forthcoming. But the reason that it works with this is because it's in reference to the already known terrestrial elevation for it. So we can, like, that's how it would work. To just do like a raw in the star off the sky, we'd have to have a physical elevation to associate it with. And as far as I know, like, well, I've got some ones I could plug in, but I haven't done that yet. And you just reminded me with your question. So thank you very much for that. I will let you know next week how that turns out. Because I've got some
Could that
suspicions.
be done with an airplane?
I would imagine you could do it with the moon, right? Don't you think?
No, because it would be no. You need like an elevation to compare it to. Is what I'm saying. You couldn't just use any old thing.
So what about a plane?
What about a plane? If you knew the elevation and you backwards derived it from that,
Yeah.
and you had so okay. So if you had the coordinates of the plane and the elevation difference between you and the mountain, so you just had the angle. I don't see why it wouldn't. If you had the because it would
Right?
just be the same
I
thing.
think
If you
that would
have
be pretty
the
cool too.
yeah, if
have
you have
different
this,
heights for the plane.
well, it would so it wouldn't be the same kind of comparison because the triangle would be you would be using like the known thing of the elevation to get the other thing, and then your angle would just be whatever angle
peaks.
like whatever your angle would be arbitrary. It wouldn't be independent. It wouldn't be dependent on a specific factor. So the trick would probably work out exactly.
Got you.
He's asking a good question. Why not use 45 degrees in elevation? Because we're using mountain occlusions, and to get a 45-degree angle, your distance to the mountain would be indistinguishable from a flat Earth drop over distance. You'd be right next to the mountain.
You're like 2 miles from the mountain, looking right up.
Yeah. We did one at 5.4 miles away from a mountain, and our elevation, so the angle came out to be like 10 degrees and 57 arc minutes or something like that. And then the globe prediction was 10 degrees, 57 arc minutes, and the drop over distance was like 6 meters. So that's why. Go ahead.
Do you agree there's a marine layer that refracts light that close to the horizon?
Sure.
All right.
Yeah. I don't dispute any types of really like actual refraction mechanisms, right? But like we're testing the amounts that they say specifically, and like it just so happens that they're like 2xing and 3xing correcting to make it appear like the Earth is flat while acting like it's a globe.
Dude, what we're really differentiating is optical versus physical.
Higher? Is the refraction making it appear higher than its actual position?
Yeah. So they'll predict like 200 meters in drop, for example, and then their celestial refraction correction will be double or triple that in lift, because you can use the same ratio to figure out what it would be in lift, and it comes out to be 240. So they just like canceled out their entire drop and then added 40 meters on top of it.
All right. So if Earth were flat, then the elevation angle to the mountain would have been 2 degrees 31 minutes, no refraction. Now there is refraction happening, so it would be higher than that. It wouldn't be 2 degrees 19. It wouldn't be 231. It'd be refracted up.
Well, it's funny you mentioned that, because we predict a raw 231, just off the values, but the actual occlusion, and this is consistent through a multitude of stars, not just the one that I added. The actual occlusion angle with respect to the peak comes out to be 232 to 234. Actually, I think the highest was 236. So it's like you can see the effect of refraction within that, but so it is a little higher, but yeah, it's not what the refracted globe predicts it is. They predict like 218 or 222 depending on your refraction that you do. So theirs is always lower.
That was the measured angle to the mountain with a real theodolite, 2 degrees 19 minutes.
That is the optical angle.
All right, that's
Good
it.
thing we don't use it for anything, right? Good thing that's not used to produce the mutually exclusive
Yeah.
angle or anything.
But
Good thing it's completely unrelated to
Right.
the entire method. I'm
Is
glad
it-
we keep talking about it, though. It sure is
Well-
helpful.
No, it's fine because when you get that angle though, and you derive distances and elevations based off of the same method that we're doing, the raw flat Earth prediction to that mountain from our location comes out to be what actually, that is the actual physical elevation. So the way that it looks optically doesn't derive your position or physical elevation to the mountain the way that it does when you reference the true position occlusion timing with respect to the mountain peak.
Right. Gets
So
lost when we're trying to discern physical versus optical.
Yeah. So in other words, the physical light source is the true position. You could think of it that way. And the mountain peak that does the occluding has to be the physical peak. It can't be the refracted peak. So if it's higher, then that's mutually exclusive because there's no way that the peak on a flat Earth could also be the lower peak, right? Like it's either going to be one or the other. And those correspond to different times for physical intersections. So there should be no physical relationship to the raw trigonometric angle and the true position of the star with respect to our position at 50,000 or 50,000 meters away.
I have one more question, honestly, if you're willing.
Yeah, go ahead.
All right, so we got a bunch of distances between geographical positions of stars when they appear directly overhead, right? I can take an elevation angle to a star that someone else sees in South America, and it's going to comport with the 1 degree per 69 miles. If I'm on an A.E. Gleason's map, it kind of doesn't, like, are you guys still promoting A.E. Gleason's, or is there something else now?
The A.E. Gleason's map is just a projection. I'm not quite sure what your question is in relation to our celestial theodolite method, because if you're internally using the graticule system through celestial navigation by taking elevations to stars and making a circle of equal altitude and all that, obviously that's going to be consistent. That's what the system is based off of. But the way that we're testing it through physical occlusion angles and raw trig shows that the backbone of the actual graticule has nothing to do with the Earth being curved. It has to do with the sky being curved apparently, and then adjusting the positions of the stars to where they need to be to fit 15 degrees per hour so that they could use the graticule.
Perfect.
All right, and we'll go ahead and wrap up on that.
All right.
I'll be back in a few while I do the outro here. All right, everyone. Thank you for tuning in to Celestial Theody update number 14. We're about 2 hours in here. We're going to wrap up. I'm getting a little tired, getting a little cranky. I do apologize earlier. Got a little snappy. But the obfuscation at this point for the amount of work that I'm putting in to just be I find it just disrespectful at this point, and it's insane. It's just like when confronted with actual evidence, all of a sudden no one wants to deal with it. But anyway, I'm sorry about the personal gripe there. Thank you all for listening in and participating. Shout out to the lads in the chat holding it down. I see my boy Goose out there, my boy Bogan, Shalom Shire, Zetetic out there, Toby, Tobetheus Maximus Decimus Meridius, Ion's Cat. Who else we got out there? Bill Hickok. We got a press. Shout out to your girl. Got James Brown holding it down. I don't know what that means. That's pretty rhymey. We got Nominal, Jeff. Shout out to the lads. Mudflood. Who else did I miss? I missed Dalibor Sterka. Shout out to you. Tony Coriolis and Robert Kelly. Shout out to the lads holding it down in the chat. We'll see you guys. What are we doing tomorrow? We're doing a presentation on something or other. We may have a special guest presentation tomorrow on the history of the Royal Society given to us by our boy Gilly Pong. So stay tuned for that. But if not, we'll get up to something else on Tuesday. Have a fantastic week, everyone. See you guys tomorrow.